Good afternoon. My name is David Tonner. I am the Chief Executive Officer for Diversified Well Logging. I appreciate the opportunity that SPWLA has given us to talk about AI surface measurement while drilling. So what is that exactly? Well, we're in the business of taking drill cuttings and mud gas measurements. We believe they are messengers sending vitally important information from the subsurface to the surface, and our mission, should we choose to accept it, is to try and extract the maximum value of the information that they contain. So we do that by analyzing the elemental composition of the rock. You can see over here Goldsmith's classification of elements, and we take the data sets and we use it to generate a model mineralogy. We also have models for organic richness, TOC, grain density, porosity, and rock mechanical properties and facies. We also believe very much that the future is automated, and so I'm going to talk a little bit about what we call RoboLogger to get higher resolution depth collection even at very high ROPs. And in doing so, we can significantly reduce operational risk and cost, and also reduce the carbon footprint. So several benefits to this particular data set. So let's talk about the practicalities of how we deliver this. The first thing is, do we know that the drill cuttings are even coming from the depths that they think that they're coming from? Big question, right? Because if our depth control is not right, then any sort of data interpretation that we make on those rocks has some significant flaw in terms of integrating it with other data sets, well logs, seismic, etc. So a big part of the QA/QC process is to run an elemental gamma ray by adding uranium, potassium, and thorium, and comparing that to the LWD or MWD gamma ray. And obviously we're looking for positive covariance, and if there isn't, why not? And typically it's because of one of four things. The first thing could be you've got poor hole cleaning, in which case that lack of covariance is a precursor indication of potential stock pipe conditions. Or it could be that you've got cavings, which again, will lead to hole stability issues and drilling type problems, etc. It could be that the gamma ray is not calibrated properly, because remember, this is a ground truth measurement on the rock. Or it could be that the samples are not being collected or processed properly. But in any one of those circumstances, you would want to know about it quickly and fix it. In terms of precision and accuracy, there's a huge amount of rigor that goes into this program, where we compare standards, USGS, NIST standards, with ICP-MS elemental compositions every 5 samples. So we're continuously getting a read on the machine. We can see any drift on the instrument or any issues in the collection process. And again, the objective here is to nip it in the bud, fix it, so we can be sure of the quality of the information that we're collecting. This is some examples of how the data can be used. This is a project we recently did offshore Gulf of Mexico. And here you'll notice that, again, we've got a gamma ray from LWD in green, LWD, and the surface gamma ray or elemental gamma ray uranium, potassium, thorium is in red. So we're seeing some good covariance there. Also notice that the resistivity here in red with trace metals in black, you can't see it on here, are covariant positively with resistivity. So, helps us understand our petrophysical log responses, calibrate our petrophysical log responses. So that's very important. On this particular project, we'd actually done some pre-work. You can see it up here in the top right-hand corner, where we took a well drilled about 10 years ago and analyzed the drill cuttings with XRF elemental composition, and then a well drilled 18 months ago. And here we're actually looking to use the data to pick the tertiary Cretaceous boundary, which represents a significant pressure regression from about 16 pounds per gallon equivalent mud weight to a density that's lower than seawater. So, picking this casing point is critical. We actually also provided the micropaleontologist for this project, so using a combination of biostratigraphy and chemostratigraphy, we were able to provide the geoconfidence or lower the geological uncertainty to make this casing point pick successfully. You'll notice here that this black curve is actually sonic, and the entire LWD suite failed through this sequence marked by this yellow bracket here. The level of confidence that the customer had in the data that we were providing led them to decide not to conduct a bit trip for LWD failure, which on an offshore project has a significant cost saving. So, there's very much a commercial aspect to that side of the solutions that can be provided with these sort of measurements. The data set can be used to get indications of grain size using things like aluminum over zirconium ratios, where we would expect those elements which are richer in aluminum would be a proxy for clay, typically a more distal source in terms of provenance versus zirconium or silica, which can be a proxy for quartz, and closer to clastic source provenance is how we get proxies for grain size. Again, these would be needed to be calibrated against other more definitive and absolute measurements. We use things like thorium over potassium to get indications of clay speciation. In this particular instance, we can see that there are volcanic ashes identified in these sections, and that can have important implications from a wellbore stability perspective. We can also get indication of changes from illite to smectite, which can be used to better understand wellbore stability and avoid MPT associated with those sort of issues. This is a paper we presented at GCAGS in 2019, working together with Equinor. And on this particular project, seismic had indicated structural complexity, and that's exactly what they experienced. You can see here the geological formation zones going from the Anachacho in orange to the underlying Upsom in purple, and then to the Austin Chalk, and then into the Eagleford. So you can see here that we went through 3 faults, and the last fault we faulted up approximately 200 feet. It was determined that at this point we'd still have about just under 1,000 feet still to drill of the lateral, that the dog legs that would need to be introduced to get back in the target would not meet the objectives in terms of reservoir contact, completions efficiency, and production efficiency, so we geostopped the well. It's important to note that the gamma ray does not have a lot of character as you go across this this boundary. It was the cuttings measurements that provided them with the information and geoconfidence to make this decision. In doing so, saved about $600,000 in what would have been non-productive costs associated with drilling and completions. It's important to note that in terms of the workflow, that this was calibrated against a core that had resolution at 0.5 feet of measurements. We created a smoothing average of that to generate curves that we could compare the actual drill cuttings collection to, which was very important. We typically integrate all of this data into a geosteering panel. In this particular instance, it's with StarSteer. We have a group that's been together for over 10 years now, doing this and using downhole tool measurements over the last 3 years. We've worked extensively to incorporate the XRF and chemostratigraphic data into the interpretation to improve wellbore placement. And this is an example from the Marcellus, where you can see that we have the target window in green, the Marcellus in this darker red color, the overlying Geneseo in orange, and the underlying Onondaga limestone in blue. This was one of a record lateral, 22,000 feet, drilled very fast at 800 feet an hour. You can still see very good coherence between the surface gamma ray measurements and the downhole gamma ray measurements, which showed that the well had good hole cleaning and efficiency, which was obviously required, otherwise they wouldn't have gotten out to 22,000 feet measured depth. However, we can still see that there were changes in mechanical strength across this well. We integrated it with drilling data and MSE, and assisted with optimizing completion design. We also have modeled TOC, and I'll talk to you about that in just a moment, and a modeled grain density. This is an example of using the data set to improve drilling efficiencies. So this is a project from Midcon Scoop Stack. We were able to see silica over zirconium, silica over titanium, silica over aluminum ratios, giving indications of excess silica. We were able to steer the well path into an area of much lower drilling dysfunction and drilling vibration. And in doing so, we were able to complete this entire lateral in one run, which on previous wells had necessitated a bit trip, and so significant savings onshore, even more savings offshore. This is a project we did in South Texas with an operator who had a modus operandi of using standard mud logging, one well in a pad. They moved to using this XRF SMWD logging program on a 5-well pad. They were able to compare the data to fiber optic, microseismic, and well logs. It was found that the integration of the XRF data with MSE aided to characterize the reservoir heterogeneity and impacted the customization positively in terms of completion design. The overall learnings from this trial pad led to adoption of the XRF SMWD program in all 2020 wells, and that's now continued into 2021. So a good example of how to unlock the true value in drill cuttings. It has been published by many how to use elemental data, particularly trace metals like molybdenum, vanadium, nickel, chromium, as a paleo redox indicator. So, you know, they'll form, these metals form in anoxic or eusinic environments. A good reference paper here is Chemical Geology 232, 2006 by Nicholas Tribovillard. And in the inset here, you can actually see models that have been generated by ourselves in the Delaware Basin, where we've been able to compare to LECO TOC, SRA measurements, and we're able to get regressions of 0.92 in this particular case on nickel, so can be used as a pretty effective indicator of TOC. It is important to note that this is very much a basin specific calibration, so should be conducted in new areas, just like the stoichiometric mineral models that we build for mineralogy, which are calibrated to XRD. So in new areas we should collect more information, compare it to XRD to better calibrate and improve the models. This is a really good slide of information that was generated by Brian Driscoll from his UTech paper in 2019 on interpretation of high resolution of XRF data from the Bone Springs and Upper Wolfcamp in the Delaware Basin. You'll see over here on the left hand side the comparison of elemental data: aluminum, silica over aluminum, zirconium over aluminum, zirconium over chromium, and comparing that data to core photography and CT scanning on the core. What you can see is these typical turbidite fan finding up sequences. So you're going from silica rich silts and sands into a classic mudstone, and then that data set can then be used to start to plot out and create a paleoenvironmental depositional map, in this case a turbiditic fan, where you would expect, for example, these higher silica over aluminum ratios corresponding to areas close to clastic source in terms of provenance. As you move further away into more distal environments of deposition, you would expect to see a decrease in these silica over aluminum, zirconium over aluminum ratios, and that's how you can start to build it in terms of effective geomodeling to optimize well spacing and placement, and ultimately lower your finding development costs. You know, the mud gas measurement molecules are also very important. We're typically measuring C1 to C5, in some instances wider spectrum up to C10, and including inerts, helium, hydrogen, nitrogen, CO2. But what we can do with that information, particularly with rigorous QA/QC using gas well drilling methodologies, where we take some of the hydrocarbons from the chromatograph, compare it to the total gas, two independent measurements. We're looking for a good coherence. Typically they should fall within 0.8 to 1.2 compared to the reference of 1, and then with confidence in the quality of the data, we can start to slice and dice it and create fingerprints of indication of fluid type. Dark green would be heavier oils, light green, light oils, and then move orange condensates, reds would be gas. And then we can also plot those on ternary diagrams using different ratios, lights over heavies, etc., and start to get an understanding of the changes in the fluid fingerprint as we go through different sequences and sections, which we can highlight in different colors here, and start to see and understand if there is changes in fluid type, if there's compartmentalization and connectivity. So I'm going to talk here a little bit about robotics and automation. This is an example from a paper that we presented at AEPGACE in 2018. But we're using a robotic sample collection system to get beyond the issues associated with sampling quality, subjectivity of sample description, HSE risk, and also depth resolution associated with higher rates of penetration. Here we can actually see red squares are robo-logger collected samples, which was subsequently analyzed for XRF elemental composition, and then what we're comparing to the green curve is high-resolution lithoscanner data coming from the Van Gotten laboratory. So we're able to conclude that the robo-logger collected samples on depth and were representative and at a much higher collection frequency than typically is possible with collections by human beings. The next step in the technology evolution with that is to incorporate a LIBS laser so that we can actually get the real-time measurement of the elemental composition. and therefore be able to deliver the entire collection and analysis within about a 2 to 3 minute time frame, something which currently takes manually about 28 minutes based on the examples that I've just shown you previously. We're then shooting for within 20% error compared to the reference standard ICP-MS. So far, all of the results have been very encouraging, with a mean error of approximately 18%. So another important part of the technology evolution is utilizing data science, deep learning, machine learning, neural networking to build relationships between existing data sets and predictive data sets. What we've found is that when we start to use the actual rock composition of ground truth measurement and actual mud gas compositions, we can go from, in some instances, sub 0.9 regressions to regressions of 0.98. So within 2% of error and 98% of accuracy. This is an example of porosity density modeling that we recently did on a deepwater project in Gulf of Mexico. On the mud gas side, we work extensively with TIPS, Andy Pepper, Lara Heister, moving away from some of the older, more antiquated methods developed in the 60s and 80s with Pixler and Horwath, and generating comprehensive models which can take into consideration biogenic gas mixing. And we've had a lot of success in terms of predicting GOR and API gravities using this approach. I've included here some references on the XRF chemostratigraphy side. I'd like to take the opportunity to thank you for the opportunity to speak to SPWLA. My name is David Tonner, and it's been a pleasure. Thank you. Have a nice day.